I want to walk through an example of a complicated looking combination of wires here, but first I want to just remind us what we already know about the magnetic field produced by wires. So if I have a segment that goes from x1 to x2 of current I, and how it gets to x1 and x2 I'm not going to worry about for the moment, let's just say it starts there and ends there somehow, then the magnetic field is going to be mu naught I over 4 pi a, where a is the distance I am standing away from it, where the bullseye is above or the x is below, times that quantity of x2 over the square root of a squared plus x2 squared minus x1 over the square root of a squared plus x1 squared. Now, what we did with this before was we first off pointed off that the direction of the field you could find by taking a right-hand rule. If you lay your thumb so that it points in the direction the current goes, your fingers will be pointing out of the screen above it and into the screen below it. And in fact, where you're standing looking at it, the field would be pointing down right now. In any case, if I take the x1 and x2 and go to negative infinity and positive infinity with them, stretch this wire out to be an infinitely long wire, we showed that what we could get is a field that was equal to mu naught I over 2 pi r, and I could fill in all those dots to point out that it's everywhere above going out of the screen and everywhere below going into the screen. The other example we did was to talk about a current loop, and we worked on the idea that if I were standing at a height z above the center of a loop of radius r, we derived an equation for the magnetic field was equal to mu naught I r squared over 2 r squared plus z squared to the 3/2 power, and pointed out this magnetic field points in the z hat direction. If you take your fingers and wrap them around that circle, your thumb points upward, so the magnetic field kind of runs straight up like a fountain almost out of the center of that circle and comes in from below. If I drop the star down so that I'm standing right in the center of the circle now, then what I can do is take the z equals to 0, and I'll just have an r squared to the 3/2 in the denominator, which cancels the r squared up top, and I wind up with just mu naught I over 2r. So the magnetic field at the center of this loop is mu naught I over 2r. Now I'm going to take advantage of this in just a second here, but let me give you an example of a kind of complicated path, if you will. Let's imagine that I've got a current that flows in from the left side of the screen. I'm standing there at that red dot. It does a button hook, if you will. It turns a quarter turn around me and then goes off to the bottom of the page and goes on to infinity that direction. So I want to try to figure out what the magnetic field is where I'm standing right there in the center of that arc. And what I can do is break this into 3 segments and treat each of those segments as simple cases of the 2 things we just talked about. First off, let's look at that first segment that goes from infinity into 0, if you will, standing right next to me. So I have the equation for the magnetic field due to a line of current going from x1 to x2. In this case, x1 is negative infinity and x2 is 0 right beside me. And if I look at the limits on that, what I find is that the magnetic field that is produced is mu naught I over 4 pi a. Notice this is half of the magnetic field due to an infinite wire, and I sometimes refer to this as a half infinite wire, even though it's kind of meaningless to say. It goes to infinity on one side and stops at the middle, at the 0 point. Now, notice this also means if I kept on going, the other half of that, the mu naught I over 4 pi a that I would get from the other side, would get me back to having mu naught I over 2 pi a, the field due to an entirely infinite wire. And that's going to be important in just a second here. I also want to point out that the magnetic field due to this guy is going to be just the same as it would have been if it were an infinite wire, namely that is into the screen because I'm below the wire. The next step is to turn this thing on its side. So I'm going to look at this segment of wire that goes down now and point out the math is exactly the same as what we just did for the infinite wire in the x direction. This is just in the y now. So instead of talking about x1 and x2, we're going to talk about y1 and y2. So it kind of makes sense, hopefully, that the magnetic field strength I get from it should be exactly the same. It's a half infinite wire, just pointed a slightly different direction. And again, if I take the right-hand rule on this, what I'm going to find is lay your fingers on the screen with your thumb pointing downward, and you'll notice that your fingers point inward where the red dot is. So I get field pointing in there as well. These two are going to add together. They both point in the same direction. In other words, making this right turn here, in some sense, leaves us right where we were with having just an infinite wire, except for one thing, and that is this quarter turn that we're making right there. We have to add up the effect of that on our magnetic field. And to do that, what I want to do is go back and look at the loop. If I'm standing at the center of a loop, it's mu naught I over 2r. And the way we got to that, if you'll recall, involved taking an integral of d phi. Well, instead of taking the integral of d phi from 0 to 2 pi, now I'm just taking it from 0 to pi over 2, or 1/4 as much. So therefore the magnetic field strength due to a quarter loop when I'm standing at the center of it is just 1/4 of what it would be if it were a full loop. In other words, 1/4 of mu naught I over 2r. Also notice that if the current is going around this loop in the in the clockwise direction, your thumb will be pointing into the screen if you follow your fingers around the loop. So this also points into the screen, just like the other two did. So I can add all three of these together. The segment from the left screen coming in, mu naught I over 4 pi a. The segment starting at the center and going off to infinity at the bottom, mu naught I over 4 pi a. And the quarter loop, mu naught I over 8a. Put those all together and I get what the total magnetic field is. And if I wanted to at this point, I could plug in the 10 milliamps and the 5 centimeters for I and A, and I could solve this for an actual numeric value. That's not real critical to me, but I wanted to show you that I could take complicated patterns so long as they break down to special cases of the two that we've worked, the infinite wire and the loop, and I can still solve for what the magnetic field is.